now take up what are longitudinal and what are transverse waves. Let us consider here longitudinal and transverse waves. Let us take the difference between these two different types of waves. Let us remember this way. Longitudinal I take towards my left and transverse I consider towards my right. Let us now take up the differences between these two types of waves. Whether a wave is longitudinal or transverse, the identification would be very simple. One need to remember and identify two different directions to say whether the wave is longitudinal or transverse. The very first one is, what is the direction of vibrating particles? Direction of vibrating particles of the medium. In fact, we all can understand wave motion is nothing other than the disturbance, nothing other than the transfer of energy from one point to another by means of the particles which are in vibratory state. So, when we consider the direction of vibrating particles of the medium, we should look into that one first. In which direction the particles of the medium are now vibrating. Coming to the second one over here, what would be the direction of propagation of the wave? Direction of propagation of the wave. In which direction in that particular medium the wave is being propagated. So, first thing is the direction of vibrating particles of the medium, and the second one is the direction of propagation of the wave. If you observe these two directions carefully, if you find them to be parallel to each other, in other sense, if direction of propagation of the wave is just along the direction of vibrating particles of the medium, or when these two are parallel to each other, that kind of a wave we should call it as a longitudinal wave. When you observe these two directions which are mutually perpendicular to each other, then we can say that kind of a wave as a transverse wave. So, what is the first difference you need to remember over here? If the direction of vibrating particles and direction of propagation of the wave in the medium are parallel to each other, then one can say that type of a wave as a longitudinal wave. When both are mutually perpendicular to each other, then we can say that one as a transverse wave. For example, when we tune a tuning fork, the prongs of the medium, that particular source in this particular example as a tuning fork, the prongs used to vibrate to and fro like this. When the prongs are vibrating exactly in the same direction of the vibrating prongs, sound is going to be produced. That means the propagation of the wave and vibrating particles of the medium both are just parallel to each other. Therefore, what must be our conclusion? Sound waves are longitudinal in air. Similarly, when you just take a string like this, when we tie one end of the string to a fixed pole like that, and when we vibrate this one up and down like this, the wave which is being propagated, that of course is going to be seen like this. That wave is now going towards my right, but in which direction we are making the string vibrate? Up and down. That means the direction of vibrating particles and the direction of propagation of the wave both are not parallel to each other. They are perpendicular to each other this way. That is the reason why we can call such type of a wave as a transverse wave. So, transverse wave and longitudinal wave can be decided just by looking to these two directions part of it. Come to the second consideration, that is the second difference between these two. When we consider longitudinal waves, they have a unique feature. What is that unique feature? Whenever longitudinal waves are being formed, we find compressions and rarefactions which are going to be formed over there. Compression means the zone where the pressure is maximum. Rarefaction is that particular zone where the pressure is minimum. And compressions and rarefactions you will never find in any other type of a wave other than longitudinal wave. Therefore, compressions and rarefactions, the formation of these two is a unique feature as far as longitudinal waves they are concerned. Whereas, if you consider this transverse wave, crusts and troughs are going to be formed. In fact, one can understand this way, the positive peak of a wave is called as a crust, and this negative peak, that one we call it as a trough. So, what one should understand here is, these longitudinal waves can be rather propagated in terms of compressions and rarefactions, whereas transverse waves in terms of crusts and troughs. Coming to the next concept over here, the third difference you can directly understand this way. Compression, rarefaction, like that, if I take them alternately like this in a longitudinal wave, then distance between two successive compressions or successive rarefactions, we call that one as wavelength lambda. So, the definition for wavelength as far as longitudinal wave that is concerned, distance between two successive compressions or two successive rarefactions, that is what is called as wavelength. Whereas, under transverse wave when you take up, distance between the particles which are in the same phase, that is what we call it as wavelength. For example, when we consider one wave this way, the total angle in a wave is 2 pi radian. If I consider the angle here will be 0 degrees, here of course will be 90 degrees, here 180 degrees, here 270 degrees, and here once again 360 degrees. This is 90 degrees like we are taking up. Whatever we are considering like that means, when the particle vibrates, we used to take its state of vibration in terms of the angle it is making with the initial position. The angle subtended by the particle with respect to the mean position of rest, that is what we call it as phase or phase angle. One example I just give you over here, the same figure, if we take it in a different way here, you can understand what is this phase. One can consider a wave in full like this. All the particles initially were at rest on this line. Now, each and every particle has started vibrating like this. From its initial position of rest, each particle is now vibrating like this. That is what actually we are observing. This is the case. Now, considering this point, if the particle is suppose vibrating till this extent, you just join these two, this angle we call it as a phase. Suppose if the particle is moving to that extent, this angle is called phase. If the particle goes to this extent, this angle is called phase. If it is going till this extent, this angle is going to be the phase. Like that, when you consider in one crust, you will be finding the total angle as either pi radian or 180 degrees. In a trough once again, you will be finding pi radian or 180 degrees. So, what we should understand in this case, complete wave when we consider, 2 pi radian will be the total angle. That is what is called as phase in a complete wave. That is, of course, we can write it like 360 degrees as well. So, this phase concept one used to consider by taking the vibration of the particle with respect to the mean position of rest. So, whenever we consider the concept of phase there, this is the way we people used to measure. One complete circle when we consider, the total angle in that one will be 360 degrees or 2 pi radian. That itself is a complete phase which we find in the case of one complete wave. That is the concept. So, when we consider that one, the distance between two successive vibrating particles which are in the same phase, that is what is called wavelength. Now, observe carefully, this is one point where the phase angle is 0. This is another particle which we can consider it to be 360 degrees for the first wave and 0 degrees for the second wave. This is the beginning for the second wave and it is the ending for the first wave. Therefore, when I consider the beginning of the second wave into account, this point and this point both have 0 degrees phase. Therefore, we can say the distance gap between these 2 points, we call it as wavelength lambda. Exactly in the same manner, when I consider a particle here, another particle over here which is of course vibrating this way, then the distance between these 2 vibrating particles which are successive having the same angle of phase, that is also called wavelength lambda. So, what one should understand from this one? Distance between 2 successive vibrating particles which are in the same phase, that is taken as wavelength in the case of transverse wave. So, the third difference is in terms of the wavelength one should understand. Now, come to the fourth one please. These longitudinal waves you can produce in any state of matter. What do you mean by any state of matter? You can produce them in solids, you can produce them in liquids, you can even produce them in gases as well. So, in all the 3 states, right, 3 states of matter, in all the 3 states of matter, we can produce them. That means there is no such material medium in which you cannot produce longitudinal wave like. Surely you can produce them in solids, in liquids, even in gases. Whereas, when we consider these transverse waves, they only can be produced, right, firstly in solids. They only can be produced in solids, that is the point. And you can understand one more point over here, partly you can produce them in liquids. Why we are using this word partly? For example, a bucket full of water when you take and when you tap the surface of water there, you find few ripples which are formed there, no doubt. But you cannot find the entire water column producing the ripples there. Only few layers of water will produce ripples. That means transverse waves are no doubt formed, but only on the surface. Not the entire water column will produce a transverse wave like. Therefore, transverse waves cannot be produced completely in liquids. And in gases, no chance. Only in solids perfectly we can get transverse wave, and partly we can produce in few layers of the liquid, we can produce transverse waves as such. That is the next difference what we need to understand. Longitudinal waves, we can directly produce them in all the 3 states of matter, whereas the transverse waves can be produced only in the case of solids and partly in liquids. Come to the last difference. This is one of the very important differences what we have. Longitudinal waves cannot be polarized. This is one point we have to remember. Whereas transverse waves can be polarized. That is the concept. First and foremost, this concept of polarization we are aware of from wave optics. This polarization, actually speaking, it is the prime property of transverse waves, but not of longitudinal waves. Therefore, transverse waves only can be polarized. Longitudinal waves cannot be polarized. So, what is our ultimate conclusion from this one? Sound waves being longitudinal by nature, sound waves cannot be polarized. Light waves being transverse by nature, light waves can be polarized. So, sound waves cannot be polarized and light waves can be polarized. There is a wonderful theoretical question in this regard. Sound waves and light waves, when you have been asked to compare them, they both can exhibit reflection, refraction, interference and diffraction. All these four are common for both. But one particular phenomena, which of course is the polarization here, which you can observe only in transverse waves but not in longitudinal waves. Therefore, light waves can be polarized and sound waves cannot be polarized. So, these are the major differences one need to remember as far as longitudinal and transverse waves, which of course we are having in this particular context that is concerned. So, if you take what are the individual features we have got, let us now take what are the general features of a wave and how to write wave equation for a progressive wave, for a stationary wave, and what are again the differences between those two and all in continuation to this one. Let us now take up what are the general characteristics of a wave. Irrespective what is the nature of the wave, I am not talking of longitudinal alone or transverse alone, whatever be the nature of the wave, what are the basic and general characteristics for that? The general characteristics of a wave, whenever we consider, mainly on 5 different aspects we have to focus. The very first one is amplitude, that usually we represent this one by the letter A. What is amplitude means? Simply speaking, it is the maximum displacement of a vibrating particle. What do you mean by maximum displacement of a vibrating particle? Suppose if I consider a wave like this, each and every particle is vibrating whenever the wave is being formed. There will be one point in the crest and one point in the trough which is going to have the maximum amplitude, that is a maximum displacement from its mean position of rest. That is what we represented by amplitude. As far as one wave is concerned, amplitude whether you calculate in a crest or in the trough, that will be the same, unless the oscillations are damped ones. That anyhow we are going to deal with a little later. So, damped oscillations only will have variable amplitude. Otherwise, amplitude in a particular wave always will be a constant. Now, come to the second characteristic. That is what we call it as linear frequency. This linear frequency, either n we can represent it with, or nu we can write with, or f we can represent it with. So, linear frequency is nothing other than number of oscillations or vibrations made by a body in unit time. What do you mean by this unit time? In simply 1 second, that is the concept. Number of oscillations made by a body in 1 second or number of vibrations made by a body in 1 second, that is what is called linear frequency. Now, come to the third characteristic, that is time period. In fact, you can all understand directly this way, time taken for one oscillation or for one vibration whatever the time it is the body is taking to complete one oscillation or to complete one vibration, that is what is called time period. We represent that one by T. It is the reciprocal of frequency. In other words, we can say frequency into time period is equal to 1. Now come to the fourth difference over here, that is, what is wavelength? In fact, wavelength has got different definitions. Distance between two successive compressions or successive rarefactions, that in longitudinal waves. Distance between two successive vibrating particles which are in the same phase, that is in transverse wave. Distance between two alternate nodes or alternate antinodes, that is also called wavelength, that we come across in standing or stationary waves. So, whichever definition of course one can remember, one has to remember of course that to be taken up, this is what we call it as wavelength. Come to the fifth one, that is phase. Phase of course either phi or theta we used to give. This is nothing other than angle subtended by a vibrating particle, angle subtended by a vibrating particle from its mean position of rest, from its mean position of rest. That is what actually we take it as phase. To understand this phase, one can consider the reference circle once again. When we consider a particle is just here, 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 here like that, different particles we are considering on this horizontal plane. Now, each particle when it is vibrating, or you can understand when a particle P is just moving from this point A to B to C then to D and back to A, like this, suppose if it is moving. Then if the particle is here with reference to the center, how much angle this radius is making with the horizontal, that is what is called the phase. So, if you consider in this case, when the particle is at this point say x, this is a phase. When it is y at y, this will be the phase. When it is at this point b, this will be the phase. Like that when we consider in the upper half semicircle I am talking about, the total phase angle will be pi radian 180 degrees. The lower half once again is 180 degrees. If you imagine this circle to be a wave like this, that means upper half that refers to crest and lower half that refers to trough, the total phase in that particular wave is going to be 2 pi radian as such. So, this phase also is one such characteristic by means of which we used to estimate how the particle of that medium is vibrating when the wave is being formed. That is the concept. So, these are the major characteristics of a wave what one has to remember. One is amplitude, linear frequency, time period, wavelength and phase as such.